looks like we've got everybody with us. So go ahead and keep working on this, but as we work, I'm gonna do a little doodle up here at the top to kind of draw with you. Okay. So hopefully everybody started with a nice cell. We got our resting membrane potential, -70 millivolts, which is key for remembering what's happening with our electrical forces. Okay. So then as we think about potassium and sodium individually, we're going to want to remember their gradients. So we're going to remember that we have high potassium in the cell. I'm just going to label where we have high concentrations of these ions. But remember, if I write high on one side of the membrane, we're going to have low on the other side of the membrane. Maybe let's track these each in a different color. So let's have potassium be purple. Is that going to show up? Okay, that's okay. So high potassium outside the cell, or sorry, inside the cell. And outside the cell is where we're going to see high sodium. That can stay in red. So we're going to have high sodium outside the cell. So these are the two factors that are going to be driving the chemical driving force for each of these ions. So if we're looking now, starting with potassium, we have the two facts that we need in order to figure out what's going on with the actual movement of our ion, which is we're going to have a chemical gradient going out of the cell. So remember that for the chemical driving force, that's the CDF, we're always going from high to low concentration. So that's like, say we have 3 moles of potassium inside the cell, 2 moles of potassium outside the cell, we're going from high to low. So that's our chemical driving force for potassium. And as we think about the electrical driving force, all we're paying attention to for the electrical driving force is the charge on the ion or the valence. So I know that tripped a couple people up on the exam. When we're talking about the valence, we're talking about valence electrons. So that has to do with how many electrons are in that outer shell. Hopefully you remember that from chemistry. So that would take into account this charge as well as how many charges are on an ion. We haven't been talking about ions with additional charges yet, but we will see calcium, which has double the charge, as we start to talk about neurotransmitters at the end of this unit. Okay, so we're looking at the fact that the potassium is positive and our membrane potential at rest is negative. So we're going to have our electrical driving force going into the cell. So that's our EDF. That's just because our opposite charges attract. It's the only thing we need to think about when we're thinking about the direction of our electrical driving forces. So the tricky part that we then have to do is figure out the ECDF. So that's our electrochemical driving force, which is a combination of our chemical driving force and our electrical driving force. And the easiest way to just remember which direction that's going to point for our important ions for neurons is to just remember that our equilibrium potential for potassium is negative and our equilibrium potential for sodium is positive. We can then just remember, if we remember those equilibrium potentials in the context of these neurons, that our electrochemical driving force, which is the summation of all our forces on the ion, so it's what the ion will actually do, because an ion doesn't respond to any one of these forces individually, it has to respond to both these forces at once. So our equilibrium potential tells us about which direction the electrochemical driving force is pointing. So for potassium, it's It's like negative 94. So we want to make this more negative. So our chemical driving force is going to be stronger. So we're going to have our electrochemical driving force pointing out. Okay, so that's in the same direction as our chemical driving force, you'll notice. I'll label this. Okay. So that's what's going on with our potassium, and it's important that we remember as we talk about the action potential that potassium wants to flow out, wants to make the cell more negative. So that's going to be the key to understanding the series of events that happens as we propagate an action potential. When we're talking about the sodium, we have something different going on because there's different concentration gradient for sodium. But we use the same sort of process. So we're going to have our chemical driving force going from high to low. Oop, I want my red. Okay. So from high to low. So the chemical driving force for sodium is into the cell. We got our chemical driving force. Then we need to think about our electrical driving force. Remember, the only thing we need to think about for the electrical driving force is positive and negative. So sodium is positive, the inside of the cell is negative. So the electrical driving force for sodium is also into the cell. We have those opposite charges attracting. And here we see part of why our force on sodium is so strong, which is going to be part of why we see this big spike when we look at the action potential. So that the chemical driving force and the electrical driving force are feeding off of each other, speeding each other up. So we have a really strong electrochemical driving force. Sure, I'll do the label first. So a really strong electrochemical driving force for sodium, which is also going to be into that cell. So it's going to be like twice as large as either the electrical driving force or the chemical driving force. So we could also figure that out, remember that by remembering that our equilibrium potential for sodium is positive. Equilibrium potential tells us about this totality of the forces. Since it's positive, we have to have our positive ion flow into the cell in order to change that membrane potential to this positive. Okay. Any final questions about this resting membrane potential and these forces before we move into the action potential? I know we've talked about them a lot, but it's really, really crucial for what we're going into today. Okay. So hopefully that's clear. If it's not, make sure to keep practicing. My office hours are always open. Your SI leaders can help out, so can probably any of your TAs. Okay. So what we're doing today is talking about how we move from just thinking about the resting membrane potential to seeing changes in these charges that allow us to signal to other cells. So to do that, we have to start thinking about different types of electrical signals and what they do to the cell. So when we're talking about electrical signals, you should keep in mind an electrical signal is going to change the membrane potential. How long it changes the membrane potential for and how much it changes the membrane potential, even what part of the cell the membrane potential is changing in is going to depend on what type of signal we're talking about. But we're always going to see some type of change in that charge inside the cell. So we're going to see two types. The first is going to be small. It's going to happen over small distances. We're going to call those graded potentials. So graded potential is a small, little bitty charge. When we look at action potentials, we're going to see that action potentials are really large. We're actually going to see that these large charges are capable of communicating over long distances by a kind of sort of positive feedback loop. They're going to affect neighboring sections of our membrane, neighboring parts of our cell, and pass along this wave of really large charges. We're going to talk about graded potentials first, because even though they're small, even they only happen over a small amount of distance, they're actually what sets up our action potential. So they are important, even though they're little. Okay. So our graded potentials are going to start out with a stimulus. So the graded potentials are in response to something happening to the cell. So some kind of signal coming in. What happens when this stimulus touches our neuron is that we're going to see a small change in membrane potential. So we went through an example on Monday where we thought about what would happen if a neurotransmitter opened a sodium channel or potassium channel. So that's the kind of thing we want to be thinking about when we're thinking about a stimulus. We're going to want to think about a stimulus that opens some channels on that membrane and therefore either lets out more potassium or lets in more sodium, which is going to affect the charge inside the cell. So it's going to affect the membrane potential. What we do want to think about as we're thinking about graded potentials is, as we've been talking about the membrane potential, we've been thinking about like the total charge inside our cell. But when we're thinking about a graded potential, we want to realize that cells are actually more complex in shape than that. And so when we see a stimulus affect a change in membrane potential, it's actually going to start at a specific spot, right? That stimulus is going to come in on this left part of our neuron, this left part of our membrane, as an example, could come into other parts as well. And that's where we're going to start to see that change in charge. So for a graded potential, it matters actually where we're tracking that charge. We're not going to be averaging out the whole cell. And that's because these changes are really small, and we're going to see that they dissipate both over time and over distance from the charge. Okay. So the magnitude for graded potential can vary. We can have smaller graded potentials or larger graded potentials, depending on how strong that stimulus is. So depending on how many channels it opens. We are going to see that the graded potentials are spread by something called electrotonic conduction, which is to say, as we have a little bit of a charge here in this one place, it's kind of going to diffuse out and it's going to change the neighboring charges. We're going to see that as it spreads out, this magnitude decays, which is to say it becomes less. It shrinks as it spreads out. So that's what this image with these arrows from the stimulus that get progressively smaller is showing us, is that we're going to have a big effect on the membrane potential here at the spot where the stimulus is. But as that charge spreads out, it's going to affect other parts of the membrane a little less. So here we're seeing at the bottom, if we recorded the membrane potential and we put our little probe here at the site of the stimulus, we'd see kind of a large bump, right? Kind of a large charge here, kind of a large change in charge. But if we put our probe over on the axon hillock, so remember that the neuron has that shape, it's got its cell body, the soma with dendrites, then it moves into an axon hillock, and the axon that's going to be spreading our charge eventually as we talk about signaling. So if we record farther away from that site of the stimulus, we're going to be recording a smaller change in the membrane potential, because as these ions spread out, they're filling up more and more room. So the difference in charge, that change in charge, isn't really very much by the time we get really far away from the site of the stimulus. Okay. So I'm going to draw out a couple of things that we could see happening as we're thinking about these graded potentials. I get my annotation tool back up. Okay. So I do want you to kind of predict what I'm going to draw. So I'm going to try to draw a little bit slowly. But this is basically what we were talking about with our warm-up, right? So if we have a sodium channel open in response to our stimulus, we're going to go from our area, right? We remember we have high sodium outside. So here we have our high sodium. We remember that the high potassium was inside, but that doesn't matter for our sodium. But we do want to remember that we have this negative 70 millivolts as our membrane potential inside. So if we open up sodium channels, which we could also phrase as we make the membrane more permeable to sodium, or we increase the membrane permeability of sodium. Remember that one of the things about sodium is that there aren't that many leak channels for sodium. So in that cell at rest, sodium really can't follow its electrochemical driving force because there's just not enough doors in the membrane. But if we open more doors, remember our equilibrium potential for sodium is positive. So we're going to see that as we open more sodium channels, we're going to have sodium flow into the cell. So it's flowing down its electrochemical gradient, but both the chemical gradient and the electrical gradient were also into the cell. Okay. So as we flow into the cell, what we're going to see is that, say we're talking about a small graded potential here. So let's say we have some more sodium flowing into the cell. What we're going to do is we're going to add some charges, right? So if we had a little bit of sodium go in and we measured here at the site, say we increase this by 10 millivolts, so we got a little closer to that positive membrane potential for sodium. So now when we measure that point in the cell, we might be at like negative 60 millivolts. So we affected a change here on the membrane potential. We increased it, just to say we made it more positive. We didn't increase it by that much, so it's still negative overall. But it's more positive than it was before because we let in sodium. Okay. If our potassium channel opens, here we go, our circle. So if our potassium channel opens, remember that our potassium is high inside the cell. Remember that we actually had a lot of leak channels for potassium. So we already have potassium leaving the cell. But if we have even more open up, we're going to allow potassium to flow out of the cell. We remember that our equilibrium potential for potassium is negative 94. So it's going to make the cell more negative. It's going to travel in the direction that allows the cell to become more negative. I'm just going to draw two arrows here because this power of the sodium gradient is a bit stronger than this power of our potassium gradient because we already had a fair number of potassium channels. So we started out at negative 70 millivolts. Just for ease of math, we're going to draw the same number of charges leaving. So we let some potassium out, say we lose 10 millivolts. Now we're going to be a little closer to that equilibrium potential for potassium because we're subtracting positive charges. So we'll get to like negative 80 millivolts. Okay. So this is going to happen at specific locations where we open more channels. Oops, can I undo that? Okay. So each of these things is going to actually play a role in our action potential once it reaches a certain amount. So we're going to see that sodium channels opening and increasing the membrane potential, so making it more positive. We're going to see that that's called depolarization. So it's making the cell less polarized, right? Because we can see here at the beginning, it's bringing us closer to zero. That's how I like to remember it. It's kind of like removing this polarization from the cell. Although we'll see that depolarization actually does then become positive a little bit as we go towards our sodium equilibrium potential. Our potassium channels are going to open. We're going to see that called hyperpolarization if we're going down from -70, so becoming even more negative than the resting membrane potential. We're also going to see potassium channels open to cause repolarization. So repolarization is going to be after we have depolarization. So after we get ourselves close to zero, we're then going to pull ourselves back down to -70. And we'll look at the action potential in all sorts of different ways. So keep this in mind, but you don't have to have it totally solid yet. But we'll see that our repolarization is also caused by the potassium channels as we're pulling ourselves down. Okay. So the point of graded potentials is to figure out whether we have enough stimuli to make an action potential occur. So your neurons are always receiving some signals. They have to decide whether that signal is important enough, big enough to set off an action potential and fire themselves. Okay. So a thing about neurons is they have like this threshold. So there's a certain level of depolarization that's necessary for us to reach in order to set off a full action potential, which is this spike of charge. So we're going to need to allow a certain amount of sodium to enter the cell to reach a threshold that's then going to cause this sort of positive feedback loop to initiate a wave of charges. And we'll see that that threshold is actually -55 millivolts, but we'll see that actually drawn out in a little bit. Okay. When we're talking about a stimulus, so if I ask you about a stimulus, excitatory charges are charges that make a cell more positive. So the excitatory charges are going to be the ones that do depolarization. So really excitatory and depolarization, I want you to link in your mind with sodium, because they're both going to be basically sodium entering the cell, making the cell more positive than it was before. But we'll also have inhibitory stimuli. So inhibitory stimuli are going to cause hyperpolarization. So they're going to make us more negative. So if we start at -70, they'll take us down to, for example, -80. So associate in your mind the words inhibitory, hyperpolarization, and potassium. So all those concepts are linked. As we have potassium flow into the cell, we can hyperpolarize it, make it more negative, which is going to inhibit an action potential because it's going to make it harder to get to our threshold of -55. Okay, so when we're looking at graded potentials, we're going to have signals of both types potentially happening. So you get excitatory stimuli, which say, yes, 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 let's get closer to the threshold so that we can fire off our action potential, fire off a signal. But we'll also have inhibitory stimuli that say, no, 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 slow down, stop firing. And that'll be caused mainly by potassium. So those would be our inhibitory stimuli. And when we're judging whether we're going to send off an action potential or not, both of these will play a role. Okay. So our graded potentials can add up in two different ways. So graded potentials will sum in temporal summation, which is what happens when we have one stimulus and it like pokes our cell and then it pokes it again. So over time, if we receive the same stimulus close in time, so if we repeat that stimulus over and over again, quick in a row, that change to the membrane potential that we create is going to get added up because it's not going to have time to dissipate before we get another stimulus and do it again, basically. We'll also see spatial summation. So when we think about our cell, and we have a stimulus, say, here on the left and here on the right, we know that our graded potentials dissipate over distance. But if we're looking at two signals coming in like this, right? If we then measure the membrane potential here in the center of them, they'll be getting a little bit of the change in charge from here. They'll be getting a little bit of the change in charge from here as these are filtering out. And so we'll also see spatial summation. So if we measured at that point, we would have parts of these two graded potentials adding together. Okay. So spatial summation is going to happen when we have two stimuli that overlap in time, which is to say two stimuli that are happening like at the same time. And then we're measuring the membrane potential in like a third spot somewhere between our charges. And I am going to draw each of these types of graded potential summations in detail so that we can kind of look at what that looks like. So if we're thinking about temporal summation, we're thinking about a cell that's going to receive signals in quick succession, right? So we're going to receive multiple stimuli. So thinking about our cell, remember that there's high sodium outside, high potassium inside. Okay. But first I'm going to draw on our stimulus, right? So here we have a stimulus coming in. It's going to zap our cell. So something's going on. It says, hey, 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 do something. So we're going to imagine here that this is an excitatory stimulus. So one that's going to get us closer to our threshold. So an excitatory stimulus is going to allow sodium to flow in. It's going to do a little bit of depolarization. So I'll write that in here. So here we have our excitatory. And we'll have sodium flowing in. We could also have inhibitory. So we'd have potassium flowing out. I'm just telling you that this stimulus is excitatory. It's not to say that all stimuli are excitatory. If this is an excitatory stimulus, we're going to see a change in the membrane potential. So we're going to say this adds like 10 millivolts, right? So this is our change. So we're now at, yeah, like 60 millivolts, right? Negative 60 millivolts. So we went up from our negative 70. Okay. So now we're going to move to our second time stamp. Okay, so now we have our cell again. So what's happening with graded potentials is that over time they fade, right? So if we measure it at this time period when our stimulus is not firing, we're going to start to see that extra 10 millivolts start to dissipate. So for example, now maybe we're only at +8, right? So now we're going back down towards negative 70, okay? At our third time point for temporal summation, what we're going to have happen is another stimulus coming in. Okay. So we're going to talk about another excitatory stimulus in this case. So we're going to have another excitatory stimulus, just like at time point 1. Okay. We're going to pretend that this excitatory stimulus is exactly the same one as this one from T1, right? So we're still going to have our sodium flowing in. Okay. And what's happening with temporal summation is that this change in charge from our first stimulus hasn't totally dissipated yet, right? So imagine that T3 happens right after T2, right? So we have our +8 change from T2. It's in our cell already. But then we have another stimulus coming through, right? Remember that this particular stimulus, when it zaps our cell, changes us, raises us 10 millivolts, right? So if we then look at this cell in total, we can see that we're no longer just changing it by 10 millivolts, we're changing it in total. So I'll change colors so that we know it's our total. Cool. Okay. So we've now changed it by 18 millivolts, right? Okay. So we have a total change that's greater than any of these 1 changes. So, so we'll be even farther away from -70 at T3 than we were at T1. Okay, so if we do the math, we're going to see that we are now 18 away. So we will be at -52. So now if we measure our cell, at -52. So that's temporal summation when we have 2 signals that happen in quick enough succession that the change from the first one doesn't totally dissipate before the second one takes effect. Questions about temporal summation before we move on to spatial summation?
Would this do the same thing if it was like not
Excitatory?
Yeah, if it's like the opposite, it would kind of do the same thing and make it like more negative.
Yes, yeah, that's true. And we could also do this with one charge that's excitatory and one charge that's inhibitory, potentially, in terms of summation. So we could raise it by 10, be at +8, and then have an inhibitory stimulus come in, decrease at 10. So then in total, we'd be only up 2. Sorry, only down 2. Mental math. But yeah, you'd always just add together whatever our stimuli are over time.
I have a question too. So if it's inhibitory, is it always going to be an action potential?
No, inhibitory stimuli are basically going to stop us from sending off an action potential. That's a great question. So our excitatory stimuli get us closer to sending off an action potential. Our inhibitory stimuli get us farther away. Okay. So let's move forward and look at the graded potential. Or sorry, look at the spatial summation of the graded potentials. Okay. So if we're looking at the spatial summation, we're going to want to draw a cell that's a little different in shape, just so that we can see kind of the distance between our 2 stimuli. So I'm going to draw us kind of an oblong cell here. Okay. So spatial summation, we're going to be thinking about multiple stimuli affecting the cell at the same time. So we have our same gradients acting as usual. We're starting at -70 millivolts. We have high sodium outside, high potassium inside. So if we have an excitatory stimulus come in here, right? At this point, let's say this changes our membrane potential by 10 millivolts. A thing that is true about our graded potentials is that they are decremental, so they decrease both over time and over space. So if we were to look, say at this point, about how strong that change to the membrane potential is. So let's see here at this point, we'd only have a change of +8 in our charge. And then if we were to pick up this third point kind of right here at the top of the cell, we might have a change of +6. Okay. And this is because the ions just kind of spread out. But when we're looking at this cell, because we're thinking about spatial summation, we're not just looking at our one stimulus. Actually, and I want us to keep in mind that I'm drawing you an excitatory stimulus. The reason I'm drawing our excitatory stimuli is because those are the ones that get us closer to our threshold and therefore closer to firing an action potential. So this is our excitatory stimulus. So the arrow that we're going to see is we're going to see sodium flowing in. Actually, I'll draw the sodium on its own. So blue, the stimulus here with the squiggle, and then just our arrow for sodium. So opening sodium channels, allowing sodium to flow in the way it always wants to. But then we're also going to draw a second stimulus. So the second stimulus is happening somewhere off over here, and it's happening at the same time as this first stimulus. We're also going to talk about this as being an excitatory stimulus, which means we're going to have sodium flowing in. Okay. So we'll draw our sodium flowing in here as well. I'll just draw it on this side. Doesn't really matter which side of the arrow it's drawing on. Okay. So we have our sodium flowing in. I'm going to pick a new color for writing what's happening. But we want one that's visible. Okay, we'll pick black. Okay, so at this point of the second stimulus, it would change by 10 millivolts. But as we move towards this middle point at the top, this would dissipate because our graded potentials are decremental. So as we move a little bit away, we'd only be at +8. And then we move even farther away towards that same point as the other one. It might be at +6 here as well. So this is roughly equidistant from our two stimuli. But this means if we were to stick a probe in our cell, so stick a probe and measure the membrane potential, and we're sticking our probe right here, are we going to sense how much of a change are we going to sense here, I suppose, is what I'm asking you. So
+12.
Exactly. Yeah, so we'd be +12 at this point because we're getting a little bit of the charge from this side and a little bit of the charge from that side. So that's our spatial summation. So does anyone want to go ahead and answer this question at the bottom? Why would these graded potentials that we've been drawing be unable to communicate over a long distance?
Because they dissipate.
Exactly, because they dissipate. So once they get farther away, there's none left.
So like the charge isn't like enough to get very far.
Yeah,
That's what that means.
exactly, because our axons are
Strong enough.
quite long. So if we were to remember what our neuron looks like, right, our axon is this long, skinny kind of, yeah, like rope going off to the side. So as we measure these go on further and further and further, they dissipate before they get really very far into the axon. So we're only going to see.
Kind of me getting ahead, but like,
Mhm.
is that why we have the myelination or whatever of like along the axon so that the stimulus can skip between?
A little bit, yeah. The myelination is going to affect the speed with which we spread the action potentials. Yeah, because it allows something like this to happen. But the action potential is going to work a little bit different than these graded potentials. because once we hit the threshold, our threshold voltage, instead of dissipating like this, that's going to trigger something called our voltage gated channels, which are then going to go totally crazy. So it's similar, but it's a slightly different thing that's happening there. Okay. So speaking of voltage gated channels. Okay. As we talk about the voltage gated channels, I want us to keep in mind the directions that we can see our charges changing. So here on this graph, we see our membrane potential with the blue dotted line at our resting potential. So I want us to remember that we can move closer to our equilibrium potential for sodium. So if we have sodium flowing in, we depolarize our cell. We'll also see as we talk about our voltage gated channels and the action potential as a whole, we'll see repolarization, which is when over time we return to our resting potential. So we come back down, we come back to our polarized resting potential. That'll be due mainly to potassium. We can also see hyperpolarization, which will happen at the end of our action potential. But is also what would happen in response to an inhibitory stimulus, which is when we move even farther away from -70, so even closer to our potassium equilibrium potential, so we become super negative. So whenever we're talking about one of these directions, we're referring to the resting potential as like our resting point. So we're always talking about, are we getting less polarized than the resting potential? Are we returning to the resting potential? Are we becoming even more polarized, which is to say even more negative compared to our resting potential? And as I'm showing you this, I've just drawn a little insert here about the time order these happen in, because I don't want you to get confused by this graph, because this is just telling us about the direction that defines each of these terms, but this isn't actually the order that they're going to happen when we see our action potential. So if you want to keep in mind your action potential, you want to keep in mind this little spiky curve, and we'll see that a lot as we move forward, but just remembering it here. Okay. So as we're talking about our action potential, we want to think a little bit about the different types of channels we have and where in our neuron they're located. So far, what we've been talking about are leak channels. So we've been talking about leak channels that set up our resting membrane potential. So these leak channels, they're always open. We find them throughout the neuron. These leak channels and the numbers of them, basically, like how many there are for potassium, how many there are for sodium, is what sets up that cell to be at the resting membrane potential of -70. So those are always there. They do their thing, but as we move forward and think about the action potential, we're going to be thinking about some different types of channels. When they're open, they'll work the same way. They'll let our ions through, but we'll see that the next several type of channels we're talking about are going to be gated, which means that sometimes they're closed, which means that we can open and close them in order to send different types of signals. The ones that really are responsible for our graded potentials, that's not written on here, but it is true, are our ligand-gated channels. So ligand-gated channels open or close in response to a ligand binding. And a ligand is just like a little particle that sticks to a receptor. Hopefully you've talked a little bit about receptors in your previous courses, so your prerequisites for this class. But if you haven't, a receptor is just a membrane protein that receives a signal. That signal is often a ligand. So when we're talking about those stimulus, I draw them as little zappy arrows, but what they really are particles coming in and binding to proteins in the membrane. Those proteins in the membrane are often channels that can open and then let charges flow across the membrane. So we're going to see those ligand-gated channels in parts of the neuron that receive stimuli, receive signals. The parts of our neuron that receive the signals are mainly the dendrites. So we remember the cell body kind of has this sort of starburst pattern. So those rays coming off of our cell body, those are the dendrites. So they're trying to get signals from other cells. We'll also see them in the cell body itself. So sometimes our stimuli will contact a dendrite, but sometimes they'll come all the way into the cell body, which we also call the soma. As we move forward and talk about the action potential and talk about our neuron, the one we're tracking, sending out its own signal, we're then going to talk about voltage-gated channels and calcium channels. So for the next day or two, what we're really going to be focusing on are these voltage-gated channels. And they open or close in response to changes in the membrane potential. So this is basically how we have a threshold for an action potential, why we care that there's a threshold for the membrane potential, is because a voltage-gated channel opens or closes when the cell hits a specific voltage. And in this case, the number to keep in mind is the -55 millivolts. So we'll see that there are both voltage-gated channels for sodium and for potassium. We'll see that their actions are a little different and they trigger on different kind of time scales. We'll go through how that creates our wave of the action potential. We'll see them throughout the neuron, but especially the important place to think about the voltage-gated channels are in the axon. So we're thinking about voltage-gated channels in the axon, and they happen to be especially dense in the axon hillock, which is as we move from our cell body into the axon. So we have that kind of pyramid shape starting to narrow into our axon. That little pyramid shape, that's the axon hillock. They're really dense there because that's where we have to start off our action potential. So the voltage-gated channels, associate them in your mind with the action potential. When we get to synapses, we'll also talk about calcium channels. Calcium channels are specifically for calcium. That means we're going to see them in the little fingers at the end of the axon called our axon terminals. And they're going to be responsible for releasing neurotransmitters. Okay. I think that's our time for today. So we're going to get into the action of the voltage-gated channels on Friday. And please try and take a look at the figures in your book. There's specifically a figure about the voltage-gated sodium channel. And I'd like you to take a look and start thinking about that for Friday, because sometimes it can be a little tricky to wrap your mind around, and it'll allow you to come to class with questions about that if you find it tricky. So just find a picture of the sodium voltage-gated channels, try reading the caption, and see if you can make a little sense of it before we talk about it.
Bye.
Hey.